Here we'll find the integral of x dA over r, where r is the region of x and y, such that x squared plus y squared less or equal to 2, and x bigger equal to 1. Now let's note that this is a disk centered at the origin. This is y and this is x, of radius root 2. And, well, let's change colors here. This is the line, so this is the point here, root 2, 0. And root 2 is bigger than 1. And this is the line x is equal to 1. So really where I'm integrating, this is my region R. Now, of course, we could describe that in regular coordinates, perhaps, but the idea would be to, use polar coordinates. I think it's a better idea. So let's try that. Now, the disk x or the circle x squared plus y squared is equal to 2 just can be represented by r is equal to square root of 2, whereas the line x is equal to 1, so let us remember that x is r cos theta and y is r sine theta, whereas the line x equals to 1 implies that r cos theta is equal to 1. So this implies that r is equal to secant of theta. R is equal to 1 over cos theta, which means secant theta. Now notice here that this region can be described by the radius going from the line x equal 1 to the red circle. So r is between secant theta and square root of 2. Now I need to find the two bounds for theta. Namely, I need to find the angles at which the angle at the points of intersection. Now there are many ways we can do that. Of course, one way is to equate the two equations. So if I need to find the angles, I start by looking at equalizing the radii. So r is equal to root 2 and r is equal to secant theta. This implies that r is equal to root 2 and secant theta is equal to root 2. Now, of course, there are infinitely many values of theta that satisfy this equality, but let us pick the values between minus pi and pi that satisfy this equality. Secant theta is equal to root 2. This means that cosine theta is equal to 1 over root 2. To 1 over root 2. This means theta is equal to plus or minus pi over 4. So really here, I'm looking at the sector where minus pi over 4, theta pi over 4, and r goes from secant theta to square root of 2. So I can perhaps describe my region R in this way in polar coordinates. Remember, the constants are always outside and the functions of theta are always inside. My x is r cos theta. Now my dA, which is equal to dx dy, will be equal to r dr d theta. So in that case, I have minus pi over 4 integral from secant theta to square root of 2 of r squared cos theta dr d theta. Now I'm integrating first with respect to r, so cos theta is constant. So what do I get? I get r cubed over 3. So it's let's write this down. So I have cos theta here times r cubed over 3 from r is equal to root 2 to r is equal to secant theta d theta. And now I have minus pi over 4 to pi over 4. Let's write this here. It's cos theta. Root 2 cubed is just root 2 cubed over 3 minus cos theta times secant cubed theta over 3 d theta. Now, cos theta can easily be integrated from minus pi over 4 to pi over 4, so we'll keep this here. Cos theta, I mean, we'll do it later. And then let us simplify. Cos theta times secant cubed theta is just secant squared theta. D theta, so that's good. Now let's integrate this. An antiderivative of cos is sin. So this is root 2 cubed over 3. It's easy to convince ourselves that when we integrate cos from minus pi over 4 to pi over 4, we get 2 times sin pi over 4 minus an antiderivative of secant squared is tangent. From pi over 4 to minus pi over 4. So what do we get here? We get root 2 cubed times 3. Sine pi over 4 is 1 over root 2 minus 1/3. Here it's easy to see that this is going to be tangent pi over 4 minus tangent minus pi over 4. So this is going to be 2 tangent pi over 4. You know, you can tangent an odd function. So let's see what we get. Root 2 to cube divided by root 2. This is 2 over 3 times 2. And here this is 1 over 3 times 2. So this is 4 over 3 minus 2 over 3, which is 2 over 3.